Welcome to podcast 17.2, where we're going to be looking at the calculation and the techniques of acid-base titrations and the type of graphs that we can create from a titration. So just a quick little definition of what a titration is. When we're trying to analyze a solution, we're going to use moles, mole-to-mole ratio to figure out what an unknown concentration is. It doesn't necessarily have to be an acid-base titration, but for our purposes, that's generally what we're doing, is trying to figure out what a concentration of acid is or a concentration of base. So we use our stoichiometric equivalencies to help us figure out what the concentration of an unknown analyte is. So how do we know when we've reached the magical point when we can start doing our calculations and figure out what the concentration is? We need what is known as the equivalence point. And the equivalence point means that your moles of your acid equals your moles of your base. Now, when you have a solution, how do you know that you've reached this point? Well, there's a couple different methods. First of all, you could use some sort of color change. And generally speaking, we use an indicator of some sort. And selection of indicator we'll get into in a little bit. We use phenolphthalein quite a bit, but there's a lot of different indicators. And when the color changes, that's when we know when our moles of acid equals our moles of base. Another method that we could use is using a pH probe. Take some pH measurements and create what we call a titration curve. So you actually graph the volume of your standard compared to pH, and from that you can figure out what your equivalence point is. Now, one thing to kind of notice, or one thing to kind of put in your brain, that equivalence point does not mean it's neutral. Alright, so let's take a look at some sample titrations. So let's say, for instance, diagram number 2 for description of above experiment, and there is no experiment. So let's say, for instance, that we're going to we're trying to figure out what our concentration of sodium hydroxide might be. And so if I have a strong acid and a strong base, I would expect to create salt and water. And all of our neutralization reactions follow the same pattern where you have salt and water. Even if it's a weak acid or a weak base, you're still creating some sort of salt and water. So what the curves might look like, if you had a pH probe and your burette would give you this piece of information. Your pH probe is going to tell you, given a volume of your base, what pH are you at. You see here's our equivalence point, and some lovely little pictures that kind of show you how your moles of acid is equaling your moles of base. And what kind of indicator might you want to choose? Well, if you think of the experiences that we've already had, generally we use phenolphthalein because of the pH range at which it changes. If we created these curves, you'd notice that quickly we have this little quick uptick in the graph, and that inflection point, that midway of the inflection point, is going to be our equivalence point where we have moles of acid equaling our moles of base. As you continue the titration, and you guys have done this before, where the phenolphthalein continues to get darker and darker pink, notice that you have excess base. And so the pictures up below I like because it's got the little molecules, so you can kind of get a molecular vision of what's going on. Okay. How do we do these calculations? Oops, back it up. If we've got a strong acid and a strong base, your solution is going to end up being neutral, so your moles of acid will be equaling your moles of base. So therefore we can, instead of kind of looking at our stoichiometry, or using our ice tables, I should say, we can use a version of that M1V1, M2V2, where our moles or molarity of our acid times our volume of our acid will give us our molarity of our base times our volume of our base. For this to completely work, you'll need to make sure that your ratio between moles of acid and moles of base is a 1-to-1. And this particular calculation we can only use if it's a strong acid. So you got to know your strong acids, you got to know your strong bases. What if we've got a mixture? Weak acid, strong base, or weak base, strong acid, something like that. The neutralization reactions, in other words, you're forming water and salt, really are not an equilibrium, even though you may think of a weak acid as being at equilibrium. the equilibrium only exists after the reaction has occurred. So even though we think of an acid by itself as being in equilibrium or a base by itself as being in equilibrium, we are doing a neutralization reaction. So when I say equilibrium exists kind of after the reaction has occurred, now realize that when you're doing a titration, it's sort of an ongoing thing. So our challenge of calculating pH is we have to have a way to kind of organize all these increasing pieces of information. So far we should be pretty good with calculating pH when we just have one solution, but now we're going to be mixing solutions. So keep that in mind that these are actual reactions, not really something that's happening at equilibrium. Okay, another key is you got to obey the stoichiometry. Always start out with your balanced chemical equation. If you think about what we did with our ice boxes, we started with a balanced chemical equation. You need some sort of picture, something to give you a structure to start organizing this additional information. That's the challenge with titration. The math is not hard, it's just the ability to organize your information. You can always take a look at these in terms of a limiting reactant, excess reactant type reaction. So those BCA, the Becquerel tables that we set up a long time ago, it's exactly the same type of idea. You have to think about, put your head in the beaker, what's going on in the little flask. So I say we're going to use ice tables. I kind of change it to ICF. If you Google this, you might see ICF, because it's not at equilibrium, it's more of a final type idea. If you recognize that you have a buffer situation going on, kind of equal-ish concentrations of the acid and its conjugate base, you can also use the Henderson-Hasselbalch equation. So here's your little titration setup. Now why do I say that we could possibly use a buffer? So if we think about, let's kind of pretend this is some known, unknown acid. Doesn't really matter, whatever it is. And let's pretend that this is sodium hydroxide. So this could be acetic acid, because we're doing weak. It could be formic acid. It could be propanoic acid. Any sort of weak acid. Well, if I think of my chemical reaction, what's taking place? If I take this weak acid and my strong base, and I start to neutralize them, I'm going to create some sort of salt and water. Right? Well, if this is a salt, and generally we think about sodium because it's super soluble. If it's a salt, and of course this is all wet chemistry, this is all in water, this is going to instantly ionize into its ions. And look at this. There's my conjugate base of my acid. So really, from that first minute that this thing starts to go drippy, 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 drippy into your flask, you have created a buffer situation. So I'm going to show you how to calculate it using the ice tables, but you can always use Henderson-Hasselbalch as well if you recognize that you've got a buffer situation. Alright, so I created this little curve of my very own where we're just, with a pH probe, it's kind of reacting strong acid with strong base. And we'll take a look at how do we actually calculate the pH along these various steps. Now your equivalence point is going to be somewhere in here, kind of midway of your inflection point, where your moles of acid equals your moles of base, and we'll see if any of our calculations lead us to that point. Alright, example number 1. Calculate the pH of a 25 milliliter sample of 0.1 molar solution of HCl being titrated in the profile above. I have no reaction going on here, so to calculate the pH, this is a pretty basic calculation where you're going to take the negative log for your concentration of hydrogen ions. Since we're dealing with a strong acid, my molarity is my concentration of hydrogen ions. Sorry, I'm not writing a very straight line here. So this gives me a pH of 1. Now let me do a quick little sig fig check. So I got 3 sig figs, which means I should have 3 significant figures in my pH. So that's pretty good. Alright, number 2. Calculate the pH of the HCl now that I'm starting to add in some NaOH. So here's where the additional information starts to come in. And I say start with a balanced chemical equation. And it's okay, leave it in the molecular form. This isn't predicting products or anything. You don't have to do it net ionic. Okay, so let's start out with our chemical equation. Water and salt. Now since I'm mixing samples, volumes are always additive. So I'm adding 10 milliliters with 25 milliliters. That also means that I'm kind of diluting stuff. So what I have to do is now figure out how many moles of acid I have and how many moles of base I'm using. So I'm using the same molarity as in the previous problem. So this is a 0.1 molar solution of hydrochloric acid. If I have 25 mils of it, this means that I've got 0.0025 moles of this stuff. And my base, I've got 10 mils of 0.106 of that, which if I put that into moles gives me 0.00106 moles of NaOH. Now my ICE tables, we're going to set it up, I call it ICF, but you can call it ICE if that makes more sense to you. We need concentrations because pH is a measure, we need a measure of hydrogen ions. So I need this in concentrations. So now I'm going to have to change my moles into molarity, moles per liter. So I'm going to have to divide my moles by the total volume. So the total volume's 35 milliliters. So I divide each one of my moles by 0.035. So this gives me a new molarity of my hydrochloric acid and a new molarity of my base. So what is the pH? Well, I don't care about water because remember you can still apply your equilibrium thing. This isn't what I'm concerned about. Now let's look at this in terms of a limiting reactant. What is going to run out first? Well, my sodium hydroxide is going to run out first because I have the lower concentration of that. Yes, this side is going to go up. But for pH purposes, I don't really care about that because I need to know how much hydrochloric acid is in there. I need to know what my, there's 0 of this stuff. Because for pH I need my hydrogen ions. So now I know how much hydrochloric acid there is. In other words, how many H ions I have. So I'm going to take the negative log of 0.411, which gives me a pH of 1.386. So this should kind of make sense. You started at a pH of 1, you started to add some base to it, so now the pH is beginning to rise. We continue to titrate, drippy, 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 adding in more sodium hydroxide, and what do I end up with? So again, let's have our balanced equations. We kind of organize our thoughts, and on your paper you can probably just carry this down, but since I'm at a new slide, I will just rewrite it for you. So I add in more NaOH, meaning I'm diluting the hydrochloric acid even more. So I'm going to do the same thing, figure out how many moles of acid, how many moles of base I have, and figure out what my new molarity is. If you need some help with that little step, please make sure you come see me. There's moles per liter, but volumes are additive, so keep that in mind. So it turns out that I now have equal molarities here. And I don't care about that piece. I have none of this. So how is this going to change? Well, it's a 1-to-1 ratio, and I have equal concentrations. So guess what? They are both limiting, which means I end up with none of that, and really what I have left is salt. So if all I have left is salt, what does that tell me? pH equals the negative log of 0. Really, you can just kind of skip the math and go, my pH is neutral. This is my equivalence point. And if you kind of bounce back to your graph, that should sort of make sense where that number might be. Example number 3. So what happens? You continue to add more base. So if you're using phenolphthalein, this is where it's even going nice and dark pink. Calculate the pH. We're continuing to add in some sodium hydroxide. So what do I have now? I'm still diluting the one by the other, so I figure out my new concentration of hydrochloric acid and my new concentration of the sodium hydroxide. My salt, so this is the NaCl. I'm just assuming you can remember that we're using the same chemical equation. Have no salt. So now what is limiting in this particular case? My hydrochloric acid is limiting. Which if you think about what you've just done, you've gone past the equivalence point. So yeah, all your acid is gone. And now what you have is a whole lot of base. And what we're trying to figure out is, what does that mean pH-wise? So that's all used up. I now have 0, 1, 2, 5, and a bunch of salt. Don't need that plus. Okay, now what do I have? I have OH ions. So all I can calculate from this is my pOH. So I'm going to have to take the negative log of 0.0125. This gives me a pOH of 1.903. I'm using 3 decimal places because my givens have 3 sig figs. That's how the sig fig rule of logs applies. Now that I know my pOH, I'm going to subtract it from 14 to get my pH. And I get 12.097. Now that should make sense. I've added in a whole lot more base, so I would expect to end up with a basic pH. Now you may see lots of questions dealing with interpreting data from pH curves. So I threw a bunch of them kind of together. Most of these are going to be determined using some sort of pH probe. And what I just want you guys to kind of look at is if it's a strong acid, strong base, notice where its starting pH is compared to a weak acid, strong base. Notice where its starting pH might be. If we flip it around, say you're doing strong base to a strong acid, like you just sort of flip the what's in the burette, what's in the flask, it doesn't really matter. This is kind of what you end up with. So like I said, just notice where the differences are in terms of your starting pHs. So that kind of puts 2 of them together. These 2 curves, polyprotic acids, you won't see a ton of on the AP or IB exam, but just so you kind of see what happens, each one of these inflection points means that's where a hydrogen, the next hydrogen ion ionizes, where the next proton comes off. So oftentimes when you have information like pK2, pKa2 or something like that, that means that's the hydrogen ion that influences the pH the most. So we won't be doing one, but just in case you ever come across it, that's what a polyprotic acid one would look like. Okay, this Ka titration curve kind of comparison, where this comes in mighty handy is when you are asked to create a buffer solution. If we kind of bounce back, I'll just use this one, to what a buffer is, where you've got reasonable concentrations of the acid and its conjugate base. The buffering region of a titration curve is kind of in here, where the pH will actually equal your pKa. So you can figure out the Ka of an acid by looking at the curve as well. So if you have a question that asks you to determine or come up with a buffer for a particular situation, whatever the case may be, if you look at the exponent of the Ka, that tells you a pretty good estimate of what the pH is going to be. In other words, that the pH of the pKa, if that makes sense, of what the pH is going to be. So if you're trying to get a solution with a pH of 4, then I'm probably going to pick some sort of acid that's got a Ka somewhere in the neighborhood of 10 to the negative 4th. So you kind of look at the exponent, and that gives you an estimate of what type of pH your solution is going to end up being. So then obviously if you've got a pKa of 1 times 10 to the negative 4th, that's going to give you a pH of 4. If your Ka is 1.9 times 10 to the negative 4th, well, now you're kind of pushing it up to pH of 5. So that's how you might use those things. Indicators. So we've used the idea of we know we're done when it turns color. The pH meter would give us the probe, or the curve, but what if we've got indicators? And sometimes you might see questions that which one might be a more useful indicator. We use phenolphthalein a lot because phenolphthalein, is kind of at the top of that pH curve that we saw before. You look for the equivalence point and the pH that kind of corresponds to that equivalence point. And then you just kind of use a chart. So you'd have to be given a lot of information to answer these types of questions. But sort of generally speaking, this might be something that you would look at. So which indicator would you pick? If your equivalence point were, say, somewhere around 7, which one would you use? Or if your equivalence point were somewhere up like 9, which indicator would you use? I would, for this particular one, I would probably pick methyl red, and this particular one I would pick thymol blue, because that color change indicates that you're at that pH point. Probably for this one, phenolphthalein would be a little bit better, but given these two options, I'll go with methyl red. How do they work? Well, indicators are all buffers. They've got conjugate acids, conjugate bases, and something along those lines. If you think of the little Chatelier's principle lab that we did before, we used bromocresol green, and it was green when it was kind of neutral, but if it was an acidic solution, it was yellow, and if it was a basic solution, it was blue. And so what you kind of do is you think about, well, if I'm adding in some acid, as I increase my acid, it's going to shift my equilibrium this direction, and it's going to turn yellow. Or if I put in some base, change my colors, if I put in base, well, the base is going to start reacting with the H+ ions to form water. If I can get the right charge of hydroxide, that'd be spiffy. So if I add in base, it's going to decrease my concentration of hydrogen ions and then pushes the equilibrium to the other direction, and we would see that more blue color. So that's kind of just how indicators work.